ladies and gentlemen, class recording has started. So, yesterday, we started in on our discussion about mechanics, and like the subtitle here on the screen says, mechanics deals with the study of motion. And we talked about describing the motion of an object requires that we answer 4 questions. And yesterday we started in on the first question, right? That first question is, where is the object, right? And we learned yesterday that where is the object, the answer to that question goes by what name? What do we call where is the object? Position, okay? So we said that describing the position of an object requires that we first set the scene and kind of set the ground rules of how we're going to talk about where this object is. And we call those ground rules, or setting the scene, the frame of reference or the coordinate system. Where am I going to make sure that we all end up in the same spot, right? We talked about yesterday that describing the location of something as being next to this person is great unless you don't know where that person is, right? So we have to come up with a way to make sure that everybody gets to the same spot, even though you might not know the landmarks around it or whatever it might be, okay? We said that describing the position of an object is great until what happens? Until it moves. And so now we have to describe the movement or the change in position. And yesterday we talked about, we call that displacement, the change in position. And yesterday, I believe, we talked about this iguana, right? As he moved from one location to another, okay? In order to describe the change in the location, right, we use the notation delta x, right? Delta meaning change, and then x being that location on the x-axis, and we talk about this as like an xy coordinate plane, right? And in order to know the change in an object's position, we need to know 2 things about it, right? What are the 2 things we need to know in order to figure out the change in something? Where it starts and where it finishes, right? And so we do a little subtraction problem, x final minus x initial, and we get that the displacement of this object, in this instance, 60 centimeters. Good there? Okay. And we said that's great until this happens, right? And then it goes in the opposite direction, okay? When we do this math, I'm actually going to change something real quick because this will become relevant later. I'm going to make this, instead of 14 centimeters, I'm going to make this 13 centimeters, and so this becomes negative 66. You'll see why later, okay? But here, right, we said that this is important now because displacement is our first example of a vector quantity. Vector quantities are important because they tell us 2 things, right? Oh, you guys didn't get that part? Okay, all right, so here's where we'll leave off, okay? So, the idea that we describe the motion of this gecko differently, or this iguana differently in this picture versus this picture, right? Its motion is different. Different direction, obviously. We have to account for that in our description. So, displacement is an example of what we call a vector quantity. A vector quantity has to tell us 2 things. A vector quantity has to tell us magnitude and direction. Magnitude is a fancy word for how much or how big something is. And then direction is a not so fancy word that means direction. So vector quantities are required, especially when we start having to describe directions that things are going. Right? They're not just telling us how much of something, but also which way. that then leads us to this situation that you have down at the bottom of your page. So it says, a man starts out from his house and drives east 50 kilometers. After an hour, his car runs out of gas. He walks the next 5 kilometers east until he reaches a gas station. He sits at the gas station for 30 minutes to fill his gas can and get something cold to drink. He then walks back west 3 kilometers, but a kindly stranger gives him a ride for the remaining 2 kilometers to get back to his car. When he finally reaches the car, he drives back west 50 kilometers to arrive back at his house. So, fair question. Why did he just leave his house and then go back to his house? Perhaps he had an appointment or a date or something like that that he missed because he ran out of gas. So he missed his big connection. Exactly. So, all right. On the top of page 2 of your outline, there are 4 questions about this person's trip. I want you to take 2 minutes and discuss with the person next to you the answer to these 4 questions. I will put the story back up on the board so you don't have to keep flipping back and forth, okay? Well, let's take 2 minutes, answer these 2 questions, and then we'll come back and discuss together as a group. Oh, that's just me making a picture. All right. So, we are back recording. All right, I paused it during that time. We're back recording. Okay, so, first question. How many of us wrote this? How many of us wrote this? All right. Because displacement is a vector quantity and it needs to tell us magnitude and direction. So he went 50 kilometers, but which way did he go 50 kilometers? If you want to describe his motion, there's a big difference in him moving 50 kilometers this way versus 50 kilometers that way. Okay? Second question, displacement when he arrives at the gas station. 55 kilometers east. Yes. Okay? We said that displacement is the difference between where you started and where you finished. Okay? Next question, displacement when the kindly stranger picks him up. It's kindly. It's a kindly stranger. What? That's true. So he would just be a kind stranger? Okay. I should change it. Okay, so for this one, he did have to go back west, but displacement is the difference between where you started and where you finished. Even though he went back a little bit west, he still traveled farther east than he did west, so he's still east of his house. Does that make sense? His house being his starting point, right? And then the last question, right? What is the man's displacement for his entire trip? Technically 0 kilometers, although, you know.
But there wouldn't be like an east or anything, right?
In that case, it really, yeah, there's only one place that it would be 0 kilometers, right? So you don't have to put a direction on that necessarily. Okay? All right. Are we good with those 4 so far? Okay. Problem, though. The last question, right? What is the man's displacement for his entire trip? 0 kilometers. Well, technically that's true. That doesn't really tell the story of his day, right? I mean, it leaves out a whole bunch of information, okay? Just like you. This morning, when your alarm went off or when your mom woke you up, right? Where were you? In your bed. At the end of the day, where are you going to end back up? In your bed. That doesn't tell the story of your day, right? Well, for some people it does, right? Okay. leaves out the best part of your day, right?
Seeing Mr. Play.
This part right here. So, I mean,
Last year's my favorite. It's so warm in here. I love
it is. So, hey, at least you like being here for some reason.
Well, no, I like. Don't say it. We all know. I like you as a teacher.
All right. While displacement describes the change in position relative to the reference point, where we started versus where we ended, it leaves out the middle of the story. So we need something else to sort of fill in the gaps. That something else we refer to as the distance traveled. Distance traveled is the length of the total trip taken between a starting point and an ending point. So the length of the total trip taken between the starting point and the ending point. So when we're talking about the length of the total trip, we are disregarding which direction we're traveling. It doesn't matter whether we're going east, west, north, or south. All we're doing is just adding up the distance that we've traveled. Kind of, yes. Here we call it something different. Distance traveled is an example of something that we call a scalar quantity. Okay? It's not scalar, scalar. Long A. And then short A, I guess. So distance traveled only tells us how much or how far did we go without regard for direction. So Jillian, based on like your comment, I will say this. Usually scalar quantities are positive. I won't say always because there are some exceptions. But usually they are because usually it is just an absolute value. Right? We don't really care whether it's this way or that way. All we're doing is adding distance. Example, my track runners, anybody? Track runners? Yeah. Anybody run the 400? The 400 seems like it kind of sucks. All right. Just, you know, yeah, the 800 seems like it kind of sucks too. Because there's only 3 people. So especially too, like at the Olympics, like when you get like high level 800 runners, that really just seems like they're sprinting for 2 laps. And that. But so the reason even more to make it feel worse, right? If you run a 400 or an 800, where do you end up? Right back where you started, right? So displacement would be what? 0. But that doesn't tell the suckiness of like running a 400, right? Okay. So, but distance traveled, being a scalar, doesn't take into account that half of the time you're going one way and half of the time you're going the other way. Which, if we simplify a 400-meter race, is basically what happens, right? Half the time you're going one way, half the time you're going the other way, you end up right back where you started. Okay? Scalar quantities, that doesn't matter. Okay? So, let's revisit our guy and his trip to the gas station with 4 new questions. Okay? Those 4 questions appear on your outline. I'll put the story back up on the board. Let's take 1 minute and answer these 4 new questions. Then we'll come back and discuss together as a group. I'll put the story back up on the board. Okay. Same story, 4 questions.
Johnny, can you let go? I don't.
All right, so. All right, so we're back. Okay. So, first, distance traveled when he runs out of gas. 50 kilometers. Okay? We don't need to say the direction, right? Because distance traveled, we just learned, is called a what? Scalar quantity, and it only tells us magnitude. It only tells us how far. Distance traveled when he arrives at the gas station. 55 kilometers. Distance traveled when I changed it in the story, but okay. 58 kilometers. And then entire trip 110 kilometers. Okay? Questions? Good there?
Yes, sir.
Okay. All right. Let's move on. First, we need to settle back in. We talked at the beginning yesterday that when we're talking about mechanics, describing the motion of an object, studying motion, there are 4 questions that we want to answer. We just talked about the first one. Where is the object? So now we got to get to the second one. The second one being, what is it doing? We know where it is now, but what is it doing when it's in that location? This part, we're going to get into a couple of different, words that sound similar, and you probably have used them interchangeably before, but they are different. So let's start off with speed. First, by definition, speed is the rate at which distance is traveled. When we describe anything as a rate, there is one factor that we always need to include. What is that one factor that we need to include when we talk about something being a rate?
Over time.
Something over time. Okay? Speed is a ratio between the distance that something moves and the time that it takes to move that distance. Anything we describe as a rate is measured over time. Speed is specifically the distance that we travel over time. So speed is the distance that an object moves and the time it takes to move that distance. Speed is a ratio. Mathematically, what do ratios look like? Fractions, right? So, if we're going to come up with a way to calculate speed, we turn it into a fraction, right? Speed is calculated by taking the distance and dividing it by the time. Distance is a length. What is the SI unit that we use to measure length? Meters. Time is time. We use that seconds, so the unit that we use to measure speed is meters over seconds, or meters per seconds. Meters per seconds is a derived unit, right? It's a combination of 2 base units, because we can't describe speed in one step. We have to take 2 measurements, right? A distance measurement and a time measurement. Good there. This tells us what's going on with that object in the position that we have described it. Real quick. Here's a picture that shows a stick figure girl running a race. I don't know. The stick figure girl kind of has a ponytail. Very small ponytail, but so. Oh, all right then. All right, so here it has given us a couple of time measurements to go along with the distance, the different distance measurements that have been shown here in the race. So to calculate the speed, we need to know two things, right? We need to know what? And
Time.
okay? So, according to this picture right here, the distance that this stick figure has traveled is how far? Well, it eventually will travel 100, but this clock only goes to 50, right? So, 50 meters traveled, and according to this stopwatch, how long has it taken to go that 50 meters? 6 seconds. No, that's pretty good clip.
I bet she could do it. Why doesn't like do when she goes far?
She's an up
All right.
town girl.
Are we good with this calculation of speed?
Yes, sir.
Okay. Now, speed is our next example of a scalar quantity. It's only telling us how fast something is going. That's the magnitude part. In this case, the magnitude is not how far, but how fast. Sometimes we need to know more than that, right? If I tell you to drive, as part of our directions, or describing a motion of a car, if I say a car is traveling 35 miles per hour on Hilliard, that's great. But does that really describe what the car is doing?
No.
Right? We're missing something. What else are we missing? Which way it's going, right? So, speed only tells us how fast. It's only a scalar. But there's something else that gives us more information. And that is velocity. Now, make sure speed and velocity sound very similar, but they are different. And if you don't understand the differences, when I ask you to do it, you're not going to get it right. So, by definition, velocity is the rate of displacement of an object. And again, because it's a rate, right? That means that it's a ratio between
Distance and time.
not distance,
Rate. Time.
displacement over time. Velocity is a ratio between the displacement of an object and the time it takes to cover that displacement. It all sounds very similar to speed, but it's not the same. Again, mathematically, what does a ratio look like? It's a fraction, right? So, velocity is delta x over t. Remember, delta x we use to represent the displacement, right? Because it's the change in the position. But we still measure displacement in what unit?
Meter.
It's still a length, right? It's just a length in a specific direction. So we still use meters per second to represent velocity. Okay? So, velocity is a vector quantity. And that means it has to tell us two things. What does it have to tell us? What does it have to tell us? Direction and magnitude. So, in this case, the magnitude of the velocity is how fast is it going. And the direction is which way is it going. It's like speed, but a little more descriptive. right? So the magnitude of velocity is just the speed, just how fast. He said he did. That's why I call you the Brooke before. I mean,
What are you doing?
he probably didn't hear it.
Yeah, because I was talking.
Oh, yeah, you probably wasn't paying attention. All we're doing is geometry homework. What's that picture?
One of the two. All right, so here are two pictures of our iguana friend. What? I'll show it to you. I'll show the clip. I'll show the clip to you maybe tomorrow. Yep. All right. Hey. Whoa. Hey. We still have time left today because we're on homeroom schedule, so we don't get out at 1:05. We get out at 1:07. I know it's been a good day. So let's not ruin it. Yeah. Okay. All right. So up on the board are the two pictures of our iguana friend again. Okay. They're the same two pictures from the front side. You guys didn't have the front side, but we calculated the things yesterday. Okay? But I have added clocks, stopwatches, to give you the time when the iguana was at these certain positions. Based on that information, calculate the speed of the iguana in the top picture and the bottom picture. Sorry. Calculate the velocity. My bad. Okay. Take a minute. I'll come back and we'll talk in a second. Go.
Delta X is. No, I have. I just did it.
Dude, I'm trying to round this.
Centimeters.
I'm bugged by iPhone. Alright, let's not do this song.
All right.
Phone off.
So,
This.
up on the board. Okay. I put a quick calculation. Didn't show you all the steps, but put you a quick calculation. But to give you velocities, right, you need to know displacements and times. So the first trip that the iguana takes, 60 centimeters to the right, okay? 4 seconds, 15 centimeters per second. But we said when we did the displacement, we can do this as positive. Go ahead, bro. Yes, because remember, velocity is a vector. It needs direction on it too. Now, in this case, right, what's showing the two directions of that the two directions are different here? Well, yes. What in my answer is showing that the two directions are different? The positive and negative are enough to tell one way versus the other way. But remember, the positive and negative only tells us direction. It doesn't tell us anything about how fast. Which trip is the iguana traveling faster? Negative 22 is faster than positive 15. It's just in the other direction. Okay? That's the positive and negative is the direction part of the vector quantity. Okay? The number is the magnitude part. Okay? Good there? All right, tomorrow we will collect data for our lab. There is some homework on the calendar for yesterday and today dealing with the stuff we've talked about over the past 2 days. All right?
So I can come in and take my test whenever?
Yeah.